Welcome to Topics in Electrical and Computer Engineering. This is episode number 1, and we're going to start at the beginning by talking about voltage, current, and power, and also bring in resistance. But the overall goal in this series is to try to give a good understanding and grounding in the basics of electrical and computer engineering, but also how that relates to things we use in everyday life, such as power that comes into our homes. Or, over here on the right, we have an electric vehicle, which many of us will be driving in future years, if not already. But today, we're going to start by talking about what is voltage and current and power. Now, like some of the other video series presented on this YouTube channel, material today is based on material we offer in university courses. In particular, today's material is based on an Introduction to Electrical Engineering course. However, we're going to go beyond that, as we will in future videos in this series as well. But before we get started, some words of caution that we give in our electrical engineering laboratories. As we all know, electricity can be dangerous. I really don't need to say this, but I'm going to say it anyway. High voltages, like those in electric systems, can force enough current through you, we'll talk about what current is today, that can injure or kill you. So we know this. Even low voltage sources, however, can have high energy, like in car batteries. So you got to be careful there as well. And we warn students, and I warn you, not to extrapolate beyond what we're doing here until you know what you're doing. So let's get on with it. Here's what we're going to cover today. We're going to start with the basics, and many of you already know this, but I'm going to try to provide some interesting material along the way in case you do. We're going to talk about what are current, voltage, and power, and also we'll bring in resistance. And we'll try to make this interesting by bringing in real-world applications and example values, how much voltage, how much current, power. Then we'll talk about Ohm's law, but we're not going to do this the way is done traditionally. Traditionally, there's been way too much emphasis placed on Ohm's law. In the modern world, there are much more sophisticated devices, and we talk about current voltage curves, and we'll show some of those. And that will allow us to do a little bit of circuit analysis today, as well as design. So we all come from a diverse background. Some of us may already know a lot of this material. Others maybe not as much. And the same is true of the Intro to Electrical Engineering course. Students come out of high school, and some of them have practical experience, and others do not. So we build this circuit in the first lab. We've got a couple of AA batteries here that we put in a battery holder, and then we have a clip-on that connects that to this wiring that the students have to put together, and that forms an electrical circuit. Ideally, all of these wires simply allow the current to reach the bulb. So we abstract down to the essential elements, and we show that in a schematic diagram over here on the right. And we have a switch that we can turn on, and hopefully the light will glow. And it glows because the battery has put negative charge on the bottom here and positive charge on the top. And when we close the switch, those charges, which are unlike charges, want to come together. And they do that by flowing through the wire. Now, many people make a big deal about the fact that there's actually electrons flowing in the wire in this direction, but we're not going to do that today. We're going to adopt what's called conventional current flow. And that means we're going to think of the charges as going from positive to negative around in this direction when the switch closes. So back to the main question, what is the current? It's given the symbol I, but what is it? Well, it's the amount of charge that flows from one terminal of the battery to the other in a given amount of time t. In an interesting circuit, the amount of charge that flows per unit time changes over time. And so we consider small amounts of time t and look at how much charge was transferred during those small amounts of time. So we can write it as I equals delta Q over delta t. Or if you know calculus, we sometimes abbreviate that or show that as dq dt. And that's about all we really need to understand. As we advance through our careers, the main thing we think about is the amount of current that flows. So down at the bottom, I've listed several cases. One is a traditional flashlight bulb, such as what we just talked about. And the amount of current is typically 0.3 amps. It can vary. All these numbers can vary somewhat. But 0.3 amperes is a typical current for an old flashlight bulb. In the modern world, we've been moving away from Edison bulbs towards light-emitting diodes, and a traditional little LED that glows on a device that you have when you turn it on to let you know that it's on is probably set up to flow about 0.005 amps. That's 5/1000ths of an amp, and we call that 5 milliamps. When we use a USB charger to do something like charge our phone, currents that result can be as much as, or as little as, 0.5 amps, 500 milliamps, up to 2 or more amperes. And all of these level of amperes that we're talking about can work with fairly small diameter wires. You don't have to worry too much. But when the amperes get very large, the wires may heat up too much, so you go to larger diameter wires. And in an electric vehicle in particular, you can have currents of 200 amperes or more flowing when you step on the accelerator. And so that requires some pretty big wires. Now, before we leave this slide, let's take a quick look at this graph. Before we closed the switch and made contact from the left to the right over here, no current could flow through the bulb, of course. And so the current was 0. If we assume the switch is closed at what's called t equals 0, this axis is time, and time 0 is here, then the current rises abruptly. And as we said, it settles out at about 0.3 amperes. And as engineers, we may capture that in a mathematical expression, such as I of t is 0.3 times a function called u of t, which is the so-called unit step function that goes from 0 up to a fixed value and then is constant. U of t is constant at 1, so 0.3 times 1 is 0.3. But notice what's going on here in this graph. When the switch is closed, this bulb is cold, and actually a little bit more current flows than 0.3, and then as it heats up, the current backs down to 0.3 amps. But that's a subtlety that we don't need to talk about today. Just remember these things down here. All right, so that's what current is, but what is voltage? Well, as this slide says, it's kind of complicated. It's like the pressure behind the flow. But pressure is in quotes because it's really just an analogy, but it serves pretty well. Think of the current as water flowing through a pipe, for example, and the battery as a pump, building up the pressure that causes the flow. But today we need to talk about power as well as current and voltage. And the actual definition of voltage is in terms of energy, or the work performed on the charges as they get pumped up in the battery and then flow through the circuit and dissipate as heat and light in the bulb. So I'm going to use the terms work and energy kind of synonymous here. We'll try to make the subtle distinction between the two in another slide. But that quantity is measured in something called joules, or watt seconds. Charge, we saw before in terms of current, it is in coulombs. And voltage is formally defined as the work or energy divided by the amount of charge. Where is that work taking place? Well, inside the battery, there's positive charge at the top and negative at the bottom, and the battery's trying to put more positive charge at the top and more negative charge at the bottom. And so there's work involved because it has to push positive charge against a positive plate up here. When the switch is closed, those charges want to come together. How do they come together? By going around the circuit and through the bulb. And as a given amount of charge, Q, or delta Q, flows around the circuit and through the bulb, a certain amount of work or energy is released in the form of heat and light. So over on the right, we have some example voltage values. In our simple little circuit, we had a couple of AA batteries producing a series combination of about 3 volts when we put them both in there. And the bulb is designed to work at 3 volts, meaning it will glow pretty well and it will not burn out. If you put 5 volts on it, it may glow for a little bit and very brightly and then burn out. So you got to be careful. An LED, if you put here, would also probably burn out if you put 3 volts directly across it. LEDs, as we'll see, are spec'd to run at about 1.8 volts. USB chargers are traditionally 5 volts, but some of you may now have the so-called power delivery chargers that can power your phone up very quickly, and they can put out as much as 20 volts if the phone requests that. So there's a communication that takes place across the USB connection so that you don't accidentally blow the phone up with 20 volts. And then, of course, going much higher in voltage, electric vehicles run nominally around 400 volts for many of them, although in 2023, we're starting to see a lot more that run at 800 volts. Now, if we're working with circuits and systems, a system being, for example, an automobile, or a circuit being our silly little circuit here, we may be interested in measuring the exact values at any given time. And in our Intro to Electrical Engineering course, we do that measurement in the first lab. And here's how we take that measurement. There was a wire nut connecting this side of the switch that's on this wire to this wire that goes to the bulb. But what we've done is remove that wire nut after de-energizing the circuit. And then we've routed the flow of current through a meter, an ammeter in this case, so that as current flows from the positive terminal through the switch, it now flows through the meter, and so the meter can sense how much current is going through the wire. A few caveats about what we're doing here. Current is what we call a through variable because of what we just said, and voltage is an across variable. We'll get to that in a minute. And we de-energized the circuit before we modified it. We hooked up the meter, but we got to be sure to use the correct terminal on the meter. Otherwise, we're going to blow up a fuse in the meter. And we can use a method like this for currents up to, say, a couple of amps, a few amps. But if we have larger currents, like you may have in an automotive system, we need to do it a different way. So here we are checking the voltage and current on a 12-volt battery in my car. And you can buy these things called clamp meters that you just squeeze this trigger and it opens these jaws up, and then you stick it around this wire and then release the trigger so it's as shown, and it will read out the current. And here it's 2.5 amps. This is DC current, direct current, so the polarity matters, and there's a little plus symbol right here, and you'll either get a plus or a minus in front of the amount of current read out on the meter here to know the direction of flow. In this case, the positive terminal of the battery is up here at the top. This is actually the negative terminal of the battery with some ancillary stuff on it, and the meter is clamped around that negative terminal that goes and attaches to the chassis of the car. It's reading out a positive 2.54 amps, and this says plus, and that means the current is actually going this way. So the current is actually coming in on the positive terminal, going through the battery, out on the negative terminal. And that's because the car is on and it's currently charging. Now, what about voltage? Well, that's what this meter is measuring. There are some leads not shown over here on the left, but you can see the wires. The red wire goes to the positive terminal of the battery, and the black wire goes to the negative. So we're attaching this meter, what's called across the battery terminals. And of course, they're insulated so that we're not touching the circuits. This is a 12-volt battery, so in theory that would not be a problem for us, but we always use insulated wires in any case. So this is the car battery, and it's supposed to be a 12-volt battery. So what's going on here? This says 14.58 volts. Well, that's because these are lead-acid batteries in cars, and they require something called an overvoltage to charge them. And it's usually about 2 volts. So here it's 2.5. Okay, so I hope that gives us a good feeling for examples of voltages and currents and what they are, and in fact how we measure them. Of course, pay attention to the warnings. Be careful. Know what you're doing before you do stuff. Now, the title of today's video was Voltage, Current, and Power and Resistance. So how are the voltage and current related? Well, they're related through that thing called power. And many of you may already know this formula over here on the right. Power is voltage times current. If we know the values, then we can compute the value of power. The actual mathematical derivation of that in terms of the quantities we talked about before is shown here. And I'm not going to go through that right now. Instead, let's look at the voltages, currents, and powers that we've discussed up until now. A flashlight was a 3-volt bulb, and we said it flowed a nominal of about 0.3 amps. It might be 0.27, it might be 0.39. It depends on the voltage, it depends on the bulb. But we'll call it 0.3 to keep this simple. And 3 times 0.3 is obviously 0.9. So we got about a 1-watt bulb going on there. Of course, other flashlights can have more batteries, they can have higher voltages, they can have different bulbs. But this is a nominal value. A red LED, we said, is about 1.8 volts and 0.005 amps, so that's 0.009 watts, which we sometimes call 9 milliwatts. That's actually about 1/100th of the power of the previous bulb. Now, bear in mind that this is just a little indicator bulb, and it's probably not bright enough to light your way in the dark. So that doesn't mean LEDs are that less power hungry. But they are less power hungry than traditional Edison bulbs. A traditional 5-volt USB charger that can put out 2 amps, well, that'll give you 10 watts. And finally, an electrical vehicle, depends on the voltage and how much current it's flowing, but at 800 volt system, flowing 200 amps is 160,000 watts. 800 times 200 is 160,000. If you're not familiar with kilowatts, you divide by 746 watts per horsepower, and this works out to be 215 horsepower. So not a lightning fast electric vehicle in this case, but you could have 400 amps and then you'd have 430 horsepower. So there you go. And that's one way in which voltage and current are related. Oh yeah, there's another way. Ohm's law. If you know the voltage you're dealing with and the resistance of something like a bulb, then you can compute the current as the voltage divided by the resistance. And for some things, that actually works. In particular, things called resistors, such as shown here. This is a 50 ohm resistor that's designed to be able to dissipate up to 10 watts. Remember, when we put voltage across something and current flows through it, we get power, and that has to go somewhere, so it generally is going to go out as heat if it's a resistor. Here, we've got a power supply that's putting out 5.2 volts, and about 0.1 amps is flowing. So 5.2 times 0.1 is 0.52 watts. So it's well under the 10 watt rating of this guy, and we have no problem. If we didn't have a nice power supply like this that reads out the amount of power, we can compute the power as shown on the left. There's 2 formulas. One is V squared over R for power. The other one is I squared R. And in a university setting, we would derive those after presenting Ohm's law in this form. We would substitute this equation in for I up here in the upper right, and we'd have V times V over R, which is V squared over R. And you can figure out how this one is derived the same way. And as engineers, that's how we learn to predict what's going to happen by modeling and equations. And we would likely solve many problems with lots of different resistors and configurations, etc., etc. But let's move past that right now. Ohm's law is really just a classic simplified form of wanting to know the relationship between voltage and current, or current and voltage in a device. Some devices follow Ohm's law and they're called resistors, but others do not. Here's a classic example. This is a light-emitting diode. And I went on the web and found this in what's called a datasheet for a particular light-emitting diode, SLR56X. And datasheets are invaluable when you're designing and building things or even troubleshooting things to understand how the devices work. In this particular datasheet, it actually covers several different LEDs with different colors. The red one is here. And what are we looking at? Forward voltage is on this axis and forward current is on this axis. So in our previous example, we said 5 milliamps. This is 1, that's 10. So 2, 3, 4, 5 is here. And if you come down, then you're right here. That's 1.8 volts. That's where I gave you that value from before. Now, it's not the brightest at 5 milliamps. If we want to make it brighter, we flow more current, but the curves stop. somewhere around here, because if you flow more than 20 milliamps through it, it'll burn out after a short period of time. Here you can look at how bright it is versus the current that you're using. And here is how many milliamps it can withstand at a given temperature. So let's put all these concepts together and do something useful. Let's say we have a USB powered device and we want a little glowy LED to let people know that when it's turned on. This is classically how that's done. We take an LED, such as the one we just talked about. Maybe we set it up to flow 5 milliamps. We know it's going to have 1.8 volts across it at that point. And so that's what we're designating down here. In order to make sure that more than 5 milliamps doesn't flow, we need to put a resistor in series with it. And the question is, what is the resistor value needed in that case? Well, it turns out there's something called Kirchhoff's voltage law that says the sum of the voltage rises around a loop as current flows has to equal the sum of the voltage drops. So what's a rise? A rise is when you go from negative to positive. So here we have a 5-volt rise. There's going to be some drop across this resistor as current flows through it, and then there's 1.8 volt drop across this light emitting diode. So if there's 1.8 across here and it was 5, then the voltage drop across the resistor is going to be 3.2 volts. So to pick the resistance value needed to flow 5 milliamps, we simply use Ohm's law in this form, 3.2 divided by 0.005, and that gives us 640 ohms. Turns out that's not a standard value, so we change that to 680 ohms. Is that a problem? No, that's not a problem. That just means that instead of flowing 5 milliamps, which was kind of arbitrary anyway, we're going to be flowing, say, 4.5 or something. Doesn't matter. Still going to glow at perceptibly the same brightness. When we're designing things like this and we put a resistor in, we know that it's going to dissipate some heat, so it's prudent to check and make sure that we don't dissipate more heat than the resistor that we're going to use is rated for. So we do that with power equals voltage times current, or current times voltage. So cool, we've designed a circuit. Let's see if it actually works. So here's how I did that for this particular circuit. First, I'm only using 5 volts, and this is a current limited power supply, so it can neither put out too much voltage nor too much power to be a big problem in terms of safety, but make sure you always pay attention to these rules. Here I built it on what's called a proto board, which has some little spring clip sockets that you can push leads to and connect things together. In particular, this column of connections is all one node, which on our diagram is this line right here between the positive terminal of the 5 volts, which is the red wire coming in, and one terminal of the resistor, which is this guy right here. Then the other terminal of the resistor goes to the LED, and that's connected here. Remember, all these little socket holes are tied to the same node. So when I plug these two in, they're connected together. And then the other terminal of the LED goes to the negative terminal, which completes the circuit around here. Sometimes we call that ground and give it a ground symbol. And notice the symbol on the LED, it has a directional aspect to it, so you got to make sure you get it in the right direction, and you get that information from the datasheet. So I built this up. I applied 5 volts to it, dialed in 5 volts, and this power supply actually reads out. I don't need a separate meter. It has an ammeter built in, and it reads out 0.0045 amps, which is about 0.005 amps or 5 milliamps. About what we wanted. And it's glowing. Yay! Cool. So that about wraps it up for this video. Don't want it to go any longer than it already has. In our first lab in Intro to Electrical Engineering, we cover other topics as well, including these things called Kirchhoff's current law and Kirchhoff's voltage law. And we do that by building a couple of other circuits and taking measurements along the way. For completeness, I wanted to show this slide, but for time reasons, I'm not going to go into it here. Perhaps we'll cover this in a future video. Now, if you want to know more before then, there are many other YouTube videos to watch, of course, but if you like books, here's a really good book I've recommended in classes that I've taught. This is the Amazon page, and they have a little look inside here. You can click on that and peruse the table of contents and some of the example text. I personally think this is a pretty amazing book, especially for the price. For a systems level view of engineering in general, you might take a look at something like this. It's a map of engineering. This is a YouTube video series that I found, and here's a link to it if you want, or you can just look for it on YouTube, the map of engineering. Don't know this person, but pretty cool discussions. Here's what they talk about in terms of electrical engineering and computer engineering. This is mechanical. It's interesting. They've got motors there. That's because engineering fields cross over. And that's why we all, as engineers, take things like physics and chemistry and lots of other foundational courses. Mechanical engineers have to take electrical engineering subject matter. Electrical engineering majors have to understand mechanical systems. So we take statics and dynamics and so forth. So the map of engineering and the associated video is pretty cool, discussing those sorts of things. So that's it for our video today. I hope you found it enjoyable and informative. This is actually me in a classroom talking about a radio integrated circuit chip that we designed and built for NASA. And it uses pretty much the similar theory that we cover in our senior level courses in radio design. And on this YouTube channel, there's a series called Radio Design 101 where you can learn some of that material yourself if you're interested. This is me over here on the right showing at a car show a Honda Clarity electric vehicle. It's actually a plug-in hybrid electric vehicle, and I've also got a Corvette. And the next video will cover electric vehicles in terms of the voltages and currents and powers and all of this cool stuff. That's it. I hope you've enjoyed this. We also have an associated website, ecefiles.org, if you're interested. Hope to see you in the next video.